evening, everyone. I'm Tejashree, a second year integrated MSc Physics student. I welcome you all for today's talk on behalf of the Junior Science Club. In this talk, we'll be getting an insight from the Honorable Speaker, Dr. Ananta Shivan, into some of the interesting aspects of the atomic energy program in India, with a brief introduction to the legendary nuclear scientist, Dr. Homi Jehangir Baba. Dr. Ananda Shivan is currently the director of the reprocessing group at IGCAR, Kalpakkam. He obtained his MSc in chemistry from Vaidiyar University and metallurgy from IIS Bangalore, PhD from University of Madras, postdoc from Purdue University in the US. He established reprocessing facilities for carbide and oxide fuels discharged from fast reactors and also established the facility for the production of enriched boron element. He experimented on high temperature thermodynamics, obtained carbon potential in the carbide system, and also discovered two new techniques to measure melting points. He has authorized many international journals. With his enormous knowledge and work experience, he achieved many awards. All the participants present here can drop their questions either in the Meet chat box or in the comment sections, which Dr. Ananta Shivan will address at the end of the talk. We'll also welcome queries directly addressed to Sir by the interested participants themselves through their own mics. Now, I would like Dr. Ananta Shivan to start the talk. Over to you, sir.
Thank you, Ms. Tejasvi, for the nice words of introduction. Now, straight away, without wasting your time, let me get into the talk. I'll share the PowerPoint presentation here. All right. I hope it's visible to all of you.
Yes, sir.
Yes, sir.
All right.
Go ahead.
All right.
Yes, sir.
Yeah, a sojourn into the microcosm is the title of today's talk. At the outset, my sincere thanks to the Science Club of the University of Hyderabad for having extended this warm welcome for lecturing with you. Particularly, this is a day of primordial importance to all the fraternity at the Department of Atomic Energy, for this marks the birthday of Homi Jehangir Baba, a legendary physicist, an Indian scientist who had founded the very Department of Atomic Energy of which we are all part. And without his establishing this Department of Atomic Energy, India could not have progressed thus far as one of the advanced nations in the nuclear technology as it stands today. So it's in a way paying homage to the great scientist, the legendary scientist, Homi Jehangir Baba. So normally they say the micro world, I should in fact call it as a nanocosm or the nano world, or perhaps the femto world, which is a very small space, as once Feynman had addressed and opined, there is still more room at the bottom. There is always more and more as we go down to a lower order of dimensions as far as materials are concerned. So the microcosm, or the small space of the nucleus, is of great interest to all the nuclear and atomic scientists. So we're going to dwell deep into that, looking at both the history as well as the developments that are taking place side by side. Keeping in mind the multitude of the audience and the varied domains from which they stem, I feel today I will not get into details. Instead, I'll only try to give a bird's eye view of the entire span of things. So before I get to that, let me tell you about the outline of today's talk. I would start by saying a few words about the birth of the nuclear age in the world, followed by the inception of the atomic energy program in India, which is founded by Homi Jehangir Baba. Today being his birthday, we'll speak a few words about his life as well. And then the Indian nuclear power program in its entirety with a bird's eye view. And then the unit at which I'm working for the past 30 and odd years, that's Indira Gandhi Center for Atomic Research, which is situated at Kalpakkam, and its pertinence in the context of the Indian nuclear program and in the world scenario. And also, I would like to conclude my talk by reminiscing on some of the most interesting and important moments of scientific endeavors which I had encountered at IGCAR, and then drawing some conclusions which would be of use to the student community, and by and large, the people in the audience, the students. It all started. Sorry, yeah, sorry, there's an interruption. Yeah, sorry about it. Yeah, it all started on the 29th of on the 25th of July 1945 at 5:29 a.m. in the morning, when they went on to create what's called the Trinity test at the United States. And this was the mushroom cloud that was seen during the first nuclear explosion. And both the pictures were the real pictures. The colored image, which you see on the left, was the original one that was published by the United States Atomic Energy Commission much later. And this is all available in Google. And today, as it stands, if you go to this particular spot, what you will get to see will only be a monument which is erected in memory of the great event that happened almost about 70 odd years before. That was the first time ever man came face to face with the power of nuclear energy. How much of energy had been packed into the microcosm, into the small nucleus, which we can't even see. So that was the power of science. And I'm sure most of you who are all enthusiasts in science would have read the book 30 Years of Physics That Shook the World. So all that was happening, it was a happening time. Remember, the time was 1945. And a little earlier, in 1942, on the 2nd of December, Enrico Fermi, one of the legendary physicists, all-time great experimentalist and theoretician of the 20th century, made what's called as the Chicago pile, or CP1 as it is fondly recalled today, which is nothing but a stack of graphite and cadmium plates, along with a lot of uranium rods, which are uranium spheres, so to say, which are kept inside. And with this Chicago pile, they could show for the first time that we could harness energy from the nuclear reaction. So subsequently, what followed was the Trinity test, which showed the devastating power of the nuclear bomb or the atomic bomb. So that was not of great interest to them. All that they wanted was only harnessing energy, because the world scientists, including Sir Albert Einstein, felt that nuclear energy should be put to peaceful uses. Much about the same time, something else was happening in India. In the year 1909 was born Homi Jahangir Bhabha, an Indian physicist who is considered to be the father of the Indian nuclear program, quite rightly so, on the same day as today, that is the 30th of October in the year 1909. And he is a relative, very close relative of Dinshaw Manakji Petit and Dorabji Tata, who was one of the founding members of the Tata group of industries, which exists even today. His father was a lawyer named Jahangir Harmushji Bhabha, and his mother was Meheran. He had a great passion for studies. He was a very studious student, and his parents wanted him to get educated in a British school, basically a school run by the Brits. It was still the pre-independent area, called the Cathedral and John Connon School at Mumbai. And then his aim because of his Tata connections, was to go to the United Kingdom and then pass out in the Cambridge to obtain a degree in mechanical engineering, so that he could later on join to the metallurgical firm run by the Tatas. So that was his ultimate aim, with which he passed out at the age of 15 the Cambridge senior exams with honors, and it was easy for him to make a journey to the United Kingdom to pursue his interests. But what happened subsequently was something which was extremely fantastic for the destiny of our nation. In 1927, he went to Cambridge University at England. However, rather than engineering, his main interests were in physics. Therefore, He writes back to his father in the year 1932, I seriously say to you that business or a job as an engineer is not the thing for me. It's totally foreign to my nature and radically opposed to my temperament and opinions. Physics is my line. He feels physics was his life. I know I shall do great things here. So that was a kind of thing that Baba wrote quite obviously, because that was a time when most of the great things and discoveries were happening in physics. However, in January 1933, he received a doctorate in nuclear physics. He didn't pursue his civil engineering or mechanical engineering or whatever. Instead, he pursued nuclear physics, and he published a scientific paper titled The Absorption of Cosmic Radiation, which explained the absorption and features of electron shower and the production of cosmic rays. In the year 1936, with Walter Heitler, he co-authored a paper, even today, which is one of the well-cited papers, The Passage of Fast Electrons and the Theory of Cosmic Showers in the Proceedings of the Royal Society, Series A. And this particular paper explained how primary cosmic rays from outer space interact with upper atmosphere to produce particles observed at the ground level. The numerical estimates agreed with experimental observations that were already made by Bruno Rossi and Auger. And normally the name has to be pronounced as Auger. Auger, even today we have a spectroscopy which is named after him called the Auger spectroscopy. So he worked with legends, and also from this paper he could conclude that the observations, that whatever they had made, would be actually an experimental verification of the theory of relativity proposed by Einstein a few years earlier. So we see a picture in which John Wheeler, one of the important persons who worked on nuclear fission and fusion, the Bohr-Wheeler curve is very important. All of you might have studied that, along with Albert Einstein and Homi Jahangir Baba. Well, when he came back to India in 1939, that's when the destiny turned around. He had to go back to England to pursue his interests. However, the World War II broke at the time. Therefore, he had to stay back in India. So he decided to stay back in India and pursue his research, but where to go and what to do. Then, in the meanwhile, the Indians of Science was founded by Sir C.V. Raman at Bengaluru. It was funded by the Tatas. So he went over there to pursue his research. And he had very close association with many of the senior leaders of the Congress Party, including Jawaharlal Nehru, who later, at the time, it was not independent India. Once India got the independence, Jawaharlal Nehru, as we all know, was the first Prime Minister of India. And he had very good connections with him. And he persuaded Jawaharlal Nehru that it's very important that India has a nuclear program. And in 1944, he continued his work on the cosmic ray research, and he established a unit at the Institute, Indian Institute of Science, and began to work on the theory of point particles movement. He conducted research on the nuclear weapons independently, though, in the year 1944 as well. So, because he strongly believed, and in his own words, so to say this, it is neither possible nor desirable to separate nuclear physics from cosmic rays, since these two are very closely connected theoretically. That's what Homi Bhabha felt. Well, then in 1944, so Bhabha's going back to United Kingdom was ruled out. So he started looking for greener pastures within India where he could pursue his passion of continuing his research. He thought it's very important at that point in time in India, we need to have leading institutions where physics research could be carried out, which is not otherwise the case. So therefore, he convinced Sir Dorabji Tata, asked him to fund a fundamental institute. Even today, it's one of the leading institutes in the world. We know it by the name Tata Institute of Fundamental Research. Well, these are the photographs that show the fundamental layouts of the TAFR that's being done, and all the some of the facilities, namely the cascade generator, which is all kept, which is even today existing at TAFR. All right. Shortly after India's independence, Homi Jahangir Bhabha wrote to the first Prime Minister of India, Jawaharlal Nehru, that within the next couple of decades, atomic energy would play an important part in the economy and the industry of the countries, and that if India did not wish to fall even further behind the industrial advanced countries of the world, it would be necessary to develop this branch of science. So he was very convinced about having an atomic energy program in India. That's when the Indian Atomic Energy Program was born. So convinced by his arguments, in 1948, Jawaharlal Nehru appointed him as a director of the Atomic Energy Commission. In the early days, it was called as the Atomic Energy Agency of India, for which he was the first ever director, and till his death, he continued to be the director of that commission. And subsequent to his death, it was named after Baba himself, and that's what we have today as the Baba Atomic Research Center at Trombay, Bombay. And in 1955, he organized the first UN conference on the peaceful uses of atomic energy. Even today, there's a series of conference which almost happens every 4 years, if I'm not very wrong. In 1962, he led the Scientific Advisory Committee to the Government of India and initiated a program for starting a space research in India as well. So Baba, being a very complete physicist and a scientist, his passion for science was so amazing. He didn't stop with atomic energy. He didn't stop with cosmic rays. He also wanted to explore into the space, and therefore he wanted the Indian Space Research Organization to be founded. And along with that, the Department of Space was opened up. The Department of Atomic Energy was opened up. Later on, all this together with the Department of Science and Technology has led to the growth of physics in particular and science in general in this country. So this picture shows a very rare picture in which Vikram Sarabhai and Homi Bhabha are seen together at the Tumba Research Center. However, very unfortunately, Homi Bhabha got killed in the year 1966 in a plane crash in the Alps on his way to the Geneva. Still, it's mysterious how the crash happened and so on. But the contributions of Homi Jahangir Bhabha were enormous. It is not an easy joke to have an atomic energy establishment with all its branches established, pursuing a research in a country which had not even got us independence. To think ahead of times can be done only by visionaries. Therefore, in the very recent past, it's correct to say there lived a person amongst many of us here who in all moments of time available to him thought of science and ideas which reveal the structure of matter, its grand form and beauty, and last but not the least, how he could make India, which had just then became free from the foreign control, a powerful country which derived its strength from the knowledge of science. So this is the words of Professor Devendra Lal. So in his book on remembering Dr. Homi Jahangir Bhabha. All right, so Bhabha was not just a scientist, he was an amazing artist. He had a love and passion for poetry, he had a love and passion for music, he had a love and passion even for wonderful artwork. So he thought life has to be beautiful. He respected life, he respected science, he respected creativity, he respected originality. I've heard stories wherein Homi Jahangir Bhabha built the Bhabha Atomic Research Center under the structures and the formulae and the models of the structures that existed elsewhere in France and other countries in Europe. He wanted to bring a Europe to India. That was the kind of passion Homi Jahangir Bhabha sported. So no doubt he had been a great patriot. He had made a wonderful contribution to the country, which we see in the form of Department of Atomic Energy today. Well, some of the wonderful quotations from Dr. Bhabha himself. A scientific institution, as he says, is very important. You cannot expect overnight growth of science. It's progressive. Therefore, you need to grow it like you grow a small plant. The basic idea here being, in order to get quality and achievement, you need to nurture the minds of the people. You need to understand what they are. You need to nurture and you need to allow them to grow. That's a beautiful, wonderful understanding. And the second most important thing is anything and everything can be achieved only and only when if you have a great passion for what you do. So the work that you do, whatever you're going to do, young students, tomorrow, if you're going to have a pursuit of any scientific or otherwise a business endeavor, please do it as if your life depended on it. Do it because you love it. Do it because you like it. That's what Bhabha says. All right, fine. With these few words about Bhabha, now the atomic energy establishment has been established in India in the year 1952. And since then, India had grown. So before that, what do we have today in India? What is meant by nuclear power? What do we do? And very many people have the misunderstanding that a nuclear reactor and the atom bomb are very closely related. Not at all. So before getting into that, we should understand, before understanding nuclear technology, it's very important that we understand what is meant by nuclear power. Generally, there are different sources of power, we all know. We could derive energy from any of nature's sources, like the hydroelectric source, the solar source, all from biomass, or from the photovoltaics, or from the nuclear itself. For the time being, we'll reserve our discussion to only the nuclear methods. There are basically three methods by which we'll be able to derive power from a nuclear reaction. Two kinds of nuclear reactions give out power. One is a nuclear fusion reaction. Second is a nuclear fission reaction. The fission reaction is known much more to people, much before the fusion was known. And radioactive decay is another method by which heat is produced. So essentially, till date, man has not advanced very much. In the conventional method of power production, we need to have a method to generate heat. And with the generation of heat, we'll be able to produce power. It all started with Michael Faraday. So, and from which the dynamo was discovered or invented. With the dynamo, the huge dynamos we erect and make the dynamo to rotate, we produce power. It's as simple as that. So in the nuclear reaction, there are two different reactions, fusion reaction and the fission reaction. Even among the three methods what are listed here, we'll only talk about the fission reaction. So the fission reaction produces heat. It is this heat that is being used in nuclear reactors for producing electric power. That's the bottom line of this entire projection. So now we know how electric current is produced. Electric generation means we need to make a turbine to move around. To move around the turbine, we require a fluid. We normally call it as a thermodynamic fluid. It could be either steam or by combustion of gases, or we could even simply use water, or we could use wind. So depending on how this turbine is rotated, the energy is defined as either thermal power or hydroelectric power or wind power or whatever. So in the nuclear method, the steam is produced by using nuclear heat, which is allowed to drive a turbine, which in turn is connected to a generator, which produces power. That's nuclear energy in simplicity for you. So let's have a small visual, which is fun, which is again taken from the web. So you can have a look at it. So typically a nuclear reactor will have a vessel, and here the nuclear reaction would go on, what we call as a chain reaction, and then water would be circulated around this. So the heat produced in the chain reaction will be taken away. There is one more loop of water, the blue one what you see here, which goes around, and that produces a steam. And this steam is allowed to rotate a turbine, which is connected to a generator, and the generator is connected to the grid, so which produces the power and which powers the entire places to which it's all connected. So now the only issue is this, as you know from the 12th standard onwards, it was studied that this is basically a heat engine. The efficiency of a heat engine will depend on what's called the delta T, the differential in temperature. So to always keep the differential in temperature better, for better heat efficiency, the temperature of the water that goes in has to be cooled. So for cooling that, there is an additional circuit that we call here. So this normally continues to cool it. Therefore, the amount of water we are talking about here is several millions of gallons. Therefore, it's very important that we have a huge source of water nearby any nuclear power plant. That is why nuclear power plants are always installed near huge lakes or huge rivers or oceans. That's why we always find the nuclear power plants on the banks of the oceans. So this is in simple the nuclear reactor view. So let's move on. So another apprehension we generally have is whether nuclear energy is safe or not safe. So now looking at the pros and cons of all the different forms of energy, we have different kinds of wastage that is generated by the conventional method of heating, by which we produce power. So now, if you look at this, the flue gas desulfurization, the ash that comes out of the coal industry, then you talk about the radioactive waste, and you talk about the toxic material that we produce out of the solar power, or the amount of greenhouse gases that you produced by burning wood. When you compare all this, it's quite apparent here nuclear energy is relatively very cleaner. But still, there is a major issue with the nuclear energy. The major problem is it does produce highly radioactive material which will not decay for a long time. So what are you going to do with it? That appears to be one concern for the nuclear scientists. So whatever research that's happened to the nuclear energy so far has been concentrating on finding out solutions by which we will be able to avoid the long-term radiotoxic burden to the universe at large. So otherwise, nuclear energy is one of the solutions by which perhaps it's the only solution on the commercial scale today by which you'll be able to allay the problems of arising due to the greenhouse gas emissions. So now, if you look at the cost of production of energy, again, if you look at this, nuclear energy costs a lot less. However, to establish a nuclear power plant, we need to invest a lot of money. Once you establish it, the power production cost per se for the nuclear energy is far less as compared to the coal or compared to the oil or compared to the gas, wind, or whatever. Naturally, photovoltaics and the wind are much less, but then we are not considering the production cost that's involved in establishing a windmill or in establishing a photovoltaic and so on. And even in the hydro, it's really comparable to nuclear. But unfortunately, in India, we have a serious problem. All the rivers that flow in the north are flowing in plains. Therefore, you cannot have hydel power stations. But we are very lucky in the South India. We have all the rivers flowing in the Deccan Plateau, which is a hilly terrain. But these rivers are not perennial. Half of the year, they are dry. So it's very difficult for us to sustain ourselves with hydroelectric power. Now, can we have biomass? We don't have enough oil reserves. We don't have enough coal. Therefore, energy is always very expensive for our nation, which is always power starved. Therefore, nuclear energy still continues to be one of the attractive options for a developing nation, which is power hungry like India. So now, if you look at the relative production of the different methods of power production, and then if you look at the radiational exposure that man gets because of the different methods of nuclear power production, it's very interesting to note that when you do an X-ray examination at the laboratory for your well-being, you get exposed to radiation. And when you do atmospheric nuclear testing, which doesn't happen every other year, once in a blue moon it happens. And natural sources like potassium-40, and even in Kalpakam, all the southern shores of India, we have ilmenite, which has got thorium, which has been irradiating us for millions of years. So the background radiation, even wherever you build beautiful structures with granite is basically having more radioactivity content. So natural radioactivity, even milk has got potassium-40, which is radioactive. So there is always a background of radiation. When you compare with that radiation, additionally what's being added to the country or to the world by nuclear power production is minuscule. And that's how these nuclear power plants are generally designed. Otherwise, nobody would allow these nuclear power plants to operate at all. Okay, looking at what are the power program of the nuclear power program of India. So we have 3 distinct stages in India's power production, nuclear power production. Why 3 stages? The basic problem in India is that we have very limited resources of natural uranium. There are different kinds of reactors from which you can produce power. The simplest of all of them simply uses the uranium naturally available, and with that they make a fuel with which they run a reactor. Unfortunately, the naturally available uranium has got a fissionable isotope, a fissile isotope called uranium-235, which is very, very minuscule in its quantity, which is only 0.7 atom percent, meaning only 7 atoms for every 1,000 atom of uranium would be undergoing fission. Therefore, the amount of energy that you can produce with this will be rather less. All right, even that uranium we do not have in plenty in India. So we are depending on countries like Mongolia, Australia. You might have heard of Modi ji going to our Prime Minister, going to Australia and asking for a treaty for signature for import of uranium and so on. And however, India has got lots and lots of thorium. In fact, we have the 2nd largest reserves of thorium in the world. Therefore, if we can harness the energy from this thorium through nuclear reactions, it'll be fantastic. Unfortunately, thorium cannot be straight away used in the nuclear reactors. For that, it has to be converted into another isotope of uranium, which we call as uranium-233. This uranium-233 can be gotten from thorium by using a special kind of reactor, which we call as the breeder reactor. And that's for what a center called Indira Gandhi Center for Atomic Research, where I work, has been established. Now, once this is done, with the uranium-233 that reactors like the ones in Kalpakkam would produce, we'll be able to continue to run many more reactors in the future, which will cater to the power needs for several, at least a couple of centuries for India. So this is the general strategy which was designed none other than Homi Jahangir Baba. So we have the first stage in which we'll have reactors that run with natural uranium. From this, reactors also will produce the precious plutonium, and this plutonium will be used in the second stage for the fast breeder reactors, which in turn will also be used in the third stage. In addition to the plutonium, in the second stage, these reactors will convert thorium into the fissile uranium, which will be used in the third stage. So this is the general philosophy. Now, all the reactors that are currently operating in India are being handled by a special company which belongs to the Government of India and Department of Atomic Energy. We call that as Nuclear Power Corporation of India Limited. And there are many research centers, one of which is under the Department of Atomic Energy, one of which is the Indira Gandhi Center for Atomic Research, where the technology for FBR has already been developed. And now we are at the verge of making the first commercial prototype reactor operational within the next few years. So now, currently, are we producing nuclear power? Yes. How much are we producing? This is a lot. 7,480 megawatt electrical is being produced. There are many reactors over the entire states. For instance, we have a couple of reactors at Tarapur. We have 6 reactors at Rajasthan, and we have a couple of them at Kalpakkam, which are producing power. And there are 2 at Narora, 2 at Kakrapar. Narora is near Delhi. Kakrapar, is in Gujarat. And Kaiga is again in Karnataka. And Kudangulam is in Tamil Nadu again. This is an imported reactor. Everybody knows about it. Tarapur in Maharashtra. So in Tarapur, we have 1, 2, 3, 4 reactors. Rajasthan, we have 6 reactors, and so on and so on. In all, as on today, they're capable of producing 7,480. As you and me talk, they are producing power. Perhaps we are using the power produced by these reactors as well for this Google Meet as well. So now this is the statistics showing when these reactors were commissioned, they began the commercial operation, and what is the capacity they have. Normally for the reactors, we measure the capacity of the reactors in terms of megawatt electrical energy produced, which means the heat energy that is produced by these reactors, roughly you have to multiply it by a factor of 3. 160 megawatt electrical is equivalent to 480 megawatt thermal, which means several thousand tons of coal has to be burnt, which means essentially we are avoiding green gas emissions from all the plants to that extent. Therefore, nuclear power is certainly greener and cleaner. So this is now, in addition to this, not only the power producing reactors, we have other reactors which are kind of the toys for the nuclear researchers, both chemists, physicists, material scientists, all kinds of engineering faculty. What are these reactors? Interestingly, most of these reactors are named after what looks like a feminine name. Apsara was the very first reactor which was built, very first pile. I was talking about the Chicago pile a little earlier. Like this, a small pile. Even now it's operational. It's at BARC. This reactor looks like a simple swimming pool. It's just a pool of water into which they've immersed the nuclear pile, which continues to give neutrons. And this is absolutely used only for producing neutrons and doing some material testing. There are similar other reactors like the Cyrus, Zarlina, Purnima 1, Dhruva, Purnima 2 and 3, Kamini. Kamini stands for Kalpakkam Mini Reactor, and a special type of reactor that's being in operation very successfully at Kalpakkam, which has given us the confidence in the technology of the fast breeder reactors. And this is called as a fast breeder test reactor. It's called fast because it uses very high energy neutrons. It's called breeder because it converts thorium-232 into uranium-233. Therefore, it breeds its own fuel. It's a test reactor because it's been established to test the viability of establishing the fast reactor technology. Now, this is a photograph of the very first reactor that was built and was unveiled by the first Prime Minister of India, Jawaharlal Nehru, on January 20th, 1957. So this is an amazing block which still appears at Apsara. When we all undergo the 1 year nuclear orientation training, we never fail to visit this reactor, and it's an amazing technological pilgrimage if we can have it that way. All right, there is another reactor at Kalpakkam. This is called as a Kalpakkam mini reactor. This attained criticality on 29th October 1996, 10 years after I joined Kalpakkam. This is a very small toy reactor. This is again being used for many experimentation, for taking photographs of critical components which are used in the nose cones of rockets. Most of the rockets that ISRO flew, all the components were tested here in the reactors. So this is used for shielding experiments. So this method by which you take an X-ray photography to see a crack in your bone. Similarly, X-ray photography can be taken for identifying the defects in materials. So that's called X-radiography. Similarly, instead of X-rays, if we use neutrons, it's called neutron radiography. For some special materials, neutron radiography is absolutely necessary. That's being done here. And as chemists know, the most sensitive method of even finding out picograms of an impurity in a material is by activating it, transmuting the nucleus by exposing it to neutrons. So this is called neutron activation analysis. And this is also used for calibrating neutron detectors and for several other material characterization. This reactor is even now in operation. There's another reactor, as I told you, there's a fast breeder test reactor. This is again a research reactor. Generally, reactors are classified in terms of the method or the purpose for which they are established, like the commercial power producing reactor, the research reactor, the test reactor. Sometimes they're also classified in terms of the type of materials that are used. Like, for example, if it's using thermal neutrons or slow moving neutrons, then it's called a thermal reactor. If it's using a fast moving high energy neutrons, then it is called as a fast reactor. And what kind of materials are used? If heavy water is used for slowing down the neutrons, it's called pressurized heavy water reactor. If normal water is used, it's called light water reactor. If it uses a normal boiling pressure heating circuit, water heating circuit, in which water is allowed to boil to produce a steam, then it's called boiling water reactor. Unlike that, if it allows the water to be pressurized, like in a pressure cooker, before extracting the heat, then it's called a pressurized water reactor or a pressurized heavy water reactor, as the case may be, and so on. In the special reactor, the fast breeder test reactor at FBTR, as I already told you, every reactor is a heat engine. Therefore, you need to take the heat out of the reactor. How do we take the heat out of the reactor? We can take out of the heat out of the reactor by using a fluid. It could be either water generally, or in the case of a fast reactor, it produces so much of heat that you need to have a highly conducting material. We know metals are wonderful conductors. Therefore, this uses a liquid metal to cool the reactor itself. Therefore, this is called a liquid metal cooled reactor. Sometimes it's called liquid metal cooled fast breeder reactor, LFFBR. So this is a very difficult technology. And the liquid metal that's used is a very troublesome metal, sodium, which even in the solid state, when you expose it outside, it catches fire. Therefore, extreme care is required in designing all the systems for heating, liquefying, and circulating sodium. So that means a lot of technological challenges are involved. Therefore, a lot of materials need to be developed for establishing this technology. So now, if you look at the DAE, the whole DAE cluster has got a variety of institutes, which are all research institutes. For instance, the Baba Atomic Research Center, the Indira Gandhi Center for Atomic Research, and Raja Ramanna Center for Advanced Technology are the three fundamental research institutes, which are big institutions. Baba Atomic Research Center, almost everything and anything under the sun related to nuclear technology is being researched. Indira Gandhi Center for Atomic Research is focused towards fast reactor research. The Raja Ramanna Center has accelerators, it's got synchrotrons, it's interested in particle research. The Variable Energy Cyclotron Center, as the name suggests, it's got a cyclotron. Recently, they built a medical cyclotron, which is used for many therapeutic uses of radioactive elements. The Atomic Minerals Directorate explores. They understand geochemistry. They mine everywhere to get uranium and other naturally available minerals, which are very important for atomic energy. The Global Center for Nuclear Energy Partnership, Uranium Corporation of India, Electronics Corporation of India, and Indian Rare Earths Limited. These are all the companies which are all owned by DAE. So DAE doesn't, Department of Atomic Energy doesn't mean only working for the nuclear energy alone. It also works for several material technologies and development. In fact, the very first television that was manufactured in the country was manufactured by ECIL. We used to call it the ECTV. So when electronic technology, the information technology did not explode in the early days, DAE had constituted a major portion of the researching group. Now, anyway, it's got bifurcated, and there are many more institutions which are extremely good at that. So not only that, to fund and to man all this DAE units, we need people who are highly trained. So we have the Tata Institute of Fundamental Research, which we discussed in the beginning, Saha Institute of Nuclear Physics, Tata Memorial Center, which basically works on cancer research, Harish Chandra Research Institute, which works on mathematics, Institute of Physics at Bhubaneswar, which works on fundamental physics, National Institute of Science Education and Research, NISA, which is nothing but postgraduate college education, Institute of Mathematical Sciences at Taramani, Chennai, and Institute of Plasma Research at Ahmedabad, Homi Bhabha National Institute, which is basically a university of which we are all professors and which is existing in all the units of DAE, and the Atomic Energy Education Society, which runs schools, and the Board of Research in Nuclear Sciences, which funds many of the projects, and the National Board of Higher Mathematics, as well as the University of Mumbai, DAE Center for Excellence, and so on. So we have a lot of academic institutions, fundamental research institutions, apart from basic R&D, applied R&D, nuclear technology, etc. So now, what are the kind of researchers that they do in DAE? We work on nuclear technology. We develop the steel, specialized steel that's to be used in the nuclear industry, which is not available to us because of many of the restrictions posed by the other countries. This is all developed over 4 to 5 decades of research by the Department of Atomic Energy. We brought in the zirconium technology. We brought in the beryllium technology to this country. We also brought in the boron technology to this country, of which the last one, I also had a participation and made a significant contribution to that. We have a serious group which is working on sensors, which works on robotics, nanomaterials, ceramics, glasses, composites, radiation resistant polymers, synthetic organic chemistry, bioorganic chemistry, medicinal chemistry, nuclear physics, you name it, almost they have it. If you need to have more information about what DAE does, I suggest the websites which are shown here in red can be browsed by all those who are interested. Well, now, having said so much, I thought I'll add some technical aspect to my talk based on what I experienced over the years at the Department of Atomic Energy. And right, so now basically you have to understand one thing. I've been working on nuclear fuels. So in the nuclear industry, we normally use nuclear fuels, which can be in different forms. So the nuclear fuel has to produce heat. So it is in the form of a rod. So in the rod, either we put a rod of metal inside another tube, we call it as a clad tube, or we can put little tablets, which we call it pellets, if it's a ceramic material. If it's a metal, we can melt it, cast it, make it into a rod. Whereas if it's a ceramic like porcelain, we cannot make rods out of that. Instead, what do we make? We make small tablets, and these tablets are stacked. We call them as pellets. So we also could make them into little spheres, which is like mustards, that also can be packed inside the rods. So these rods are all piled up, and then the reactor, I showed you the schematic of the reactor to begin with. It goes into the reactor core, and then it starts heating up. So now, what's going to be the reaction of this fuel material? What's going to be the temperature that we encounter? What are the chemical stability? What are the physical stability? Is all a matter of great detail. So now there are new methods, modern methods, which could be used for their fabrication. So I have worked on a few of them. So how that is related to the modern area of research? So unfortunately, I had a hyperlink which has vanished here. So I'll go instead to straight away the presentation there, and then try to show you some of the interesting photographs, or in fact videos. Please confirm if you're able to see it. Now I devised a small method. Are you able to see it?
Yes, sir.
Yeah. Just watch the video. It's very interesting. It's not too long. It's a minute. What you see here in this video is a simple chemical reaction. This is being simply done on a hot plate. I'll read again. So this is okay. Now let's have one more video. After seeing the video, let me explain it to you. Yeah, there is a caption right here. This shows UO2. The other caption shows thorium oxide. So apparently, thanks for watching that. Yeah, so let's go back to the PowerPoint again. We'll go to the slideshow mode. Yeah. So basically what you saw was a simple method by which you can produce nanocrystalline material. The nano research is catching up everywhere now. Now, if you make this small tablets I told you of ceramic materials, what are the ceramics we are interested in? Uranium oxide and plutonium oxide. They can be made in the form of nanocrystalline form. Therefore, it's easy for you to compact them and densify them. So how do you make them? By a simple synthesis, like what you saw on a hot plate. I have a mixture of citric acid and uranyl nitrate, or citric acid and thorium nitrate, which is just heated. Within minutes, I get a nanocrystalline powder, which is further processed to get the final product. So why I'm trying to tell you this is, even though nuclear technology appears to be far from your day-to-day life, it is not so. Whatever experimental science that you understand, whatever chemistry you have, whatever physics you understand, all this could be put to use in nuclear technology in multiple ways. So one simple method I showed you was the synthesis of nanocrystalline materials, which is of relevance to nuclear technology. Now, there's another interesting technique by which I told you small spheres can be made for the nuclear fuel. This again, I was involved in this. So this is a beautiful technique. Chemists will appreciate this. You make a concoction. We know what's a sol, you know what's a gel. All those who have crossed the 12th standard will know. Sol is nothing but a solid dispersed in a liquid. Gel is nothing but a liquid dispersed in a solid. So gel is more of the solid, sol is more of the liquid. It's like the coffee and ice cream. Coffee is a sol, gel is a ice cream is a gel. Simple. So now when you take a small drop of a material of a liquid containing some metal ion plus hexamethylene tetramine plus urea and nitrate, I try to push it to 90 degrees, I simply get a solid. So I just drop it across. As you see right here, the drop comes down. The moment it comes down and down and down the column, in this column I have silicon oil. So this is hot silicon oil. So the drop is falling down here. And by the time it comes out, the drop would become a solid drop. In other words, a sol will get converted into a gel. So I drop a drop of liquid out here, small amount of liquid here. What I get here is a small mustard-like gel, which is again a nuclear material. This can be used. The advantage, you don't have to touch anything. This can be remotely done. So this is very important when you handle radioactive material. So development of sol gel chemistry is a very important area where people can contribute. The same thing done in a different method. This is called another method. This is called the gel entrainment technique, in which much smaller spheres can be made. This is experimental facility which we had made in our laboratory. I'll not get into the details of it, but then I'm just showing you how exciting the research work could be. Yeah, okay. I'll not get into that. Another very important thing which I was telling you a few minutes back was production of elemental boron. Why we should work on it? Because the foreign countries are not going to give you this material because you're not signed the NPT, Non-Proliferation Treaty. Therefore, you have to find your own method. How will you do it? So there is a very difficult method which is for producing the elemental boron. Boron is a very normal chemical which is available as borax. You use it for your carom board like boric acid that contains boron. But unfortunately, that boron contains only 19% of the boron 10 isotope, whereas the rest 71% of that isotope, 81% I'm sorry, of the isotope is only B11. So this 19% has to be enriched to a much higher value, more than 60 to 80%. So that is done by a special technique, by ion exchange or by distilling a suitable compound. And from this, potassium fluoroborate containing boron 10 is obtained. This has to be converted into elemental boron. How do we do this? We take that in the form of a salt, we dry it nicely, mix it with potassium chloride and potassium fluoride, And then the molten salt along with the KbF4 is electrolyzed. So upon electrolysis, we get boron in the precipitate, in the electrode deposit. Then that deposit is taken and leached. What is so great about it? Because it's high temperature, 800 degrees, you cannot handle it just like that. And also the emanating gases are going to be fluorine. Moreover, we need to optimize the product yield, and we should get the best quality of boron without contaminants. So this is a schematic which shows it's like a furnace which is so huge. The furnace will be as tall as a person, 5 to 6 feet, and there's a retort vessel inside which a nickel vessel is lowered, into which a graphite crucible is kept, into which another graphite sleeve is put, then another cooling collar is put at the top, and then we need to cool this, of course, with water circulation, and then argon is purged through this so that whatever salt you're going to put inside again doesn't pick up moisture. Then the salt is dried up. A mixture of potassium chloride, potassium fluoroborate, and potassium fluoride are together taken and then charged inside this. And as the charge comes inside, then we close it. Then we purge again argon. We start heating it. Upon heating to about 800 degrees Celsius, first we degas again once more. Then again purge argon. Then we close it. And then we start keeping the electrode at the top. After melting the charge, we immerse the electrode, apply the potential, DC potential, and then deposit the elemental boron when chlorine comes out of the whole thing. Then this is taken out and then cooled for some time and then taken outside and then dipped into water. And inside the water, the boron precipitate falls apart. So we'll be able to take this boron precipitate that comes out. It's a black powder. This can be done. But what's so great about it? This is not a simple job. This needs to be done with the collaborative methodology. So multidisciplinary efforts are indeed warranted. We need to have mechanical engineers, electrical engineers for setting it up, metallurgists, chemical engineers, and so on. So about 30 engineers and scientists worked on it, and 60 operators from DAE were taken in. They were all trained. We developed the process. We optimized the process. And what, as a scientist, what did I get from this? During the course, we trained about 10 MSc project students. They worked on this process as well. And about 3 PhD students completed a thesis based on the problems related to this particular technology. As a result, India got a technology on boron. And this boron cannot be imported in the country, and its cost is infinite. A gram of boron costs about $2,000 and more, and even that's not available. So we produce something like 100 kilograms of the boron that's required for a reactor, which is being built in Kalpakkam within literally no time. Within about 20 days, the material was available, and then within a span of about 1.5 years, the entire boron was produced. Right. There's another very important and interesting technology which I was involved in development. Melting point of a material is a very simple thing. But then when you go to very high temperatures, beyond 1000 degrees, measuring the melting point is going to be very difficult. Many conventional techniques like differential thermal analysis cannot be used. So how do you do this? So very simple. What do you do is, we all know how it feels to be inside a room, right? Right now it's nighttime. So look at your window. Window is very dark because outside it's not illuminated. Look inside, it's fully illuminated. If you happen to look at the same window, going outside the room and then watching the window will be very bright. Now, if you have a mirror inside the room and then you go outside and watch the window, from the outside, the window will be bright. But look into the mirror, which is now you're seeing it inside the window. That window will reflect the image, that mirror will reflect the image of this window as a dark window. So similarly, when you take a cup like this and then heat it by any non-contact method like induction heating or electron bombardment heating, and put a piece of metal here, that forms a blob, which is a reflecting blob, which will reflect the image of this bright orifice as a black spot. So when it will happen? Only when the blob is formed. When the blob would be formed? Only when the metal melts. So this is a wonderful method by which you can find out the melting of a material. Why this is required? Very radioactive materials which melt at more than 1500 degrees have to be investigated, that too remotely. For this is a wonderful technique. This is developed by me. The same thing can be done at low temperatures also. That is found out during the course of the experiments that I did, that resulted in a discovery called the low temperature spot technique. I'll not go into the details of it. So typically what happens is when you run this experimentation, you see the central portion, which is like this. And in the center, you see little spots coming up. This is all nothing but the metal slowly beginning to melt. When it reaches the melting point, everything melts and then you get a simple spot. So if you can identify the temperature at which this happens, then you know the melting point. The temperature can be identified by using a pyrometer. So this is the experimental setup I established in my laboratory, and with which we could measure the melting point of many of the radioactive materials, which is again only one of its kind that exists in the entire country as of today. So we are quite okay. We are quite happy with it because we have a technology by which we'll be able to investigate very complicated materials very comfortably. Okay, so I've given you some of the problems that I worked on. I've also given you a very bird's eye view, very cursory look at the Department of Atomic Energy after narrating the life brief story about Dr. Homi Jahangir Baba. So I would like to take the lessons that was taught by one of the great mathematicians of our times, Richard Hamming, who had worked on many problems. He's no more, but then I am a great follower of Richard Hamming. He worked in the Bell Laboratory. He was a mathematician, and he had said a lot of things which I find is very common and contextually correct for us to talk about today. We could turn all our problems into opportunities, like typically in the boron case, where we had to work on a developmental program. We could have something like 13 people doing their PhDs and MScs. So look into the problem where you can work on. That's very important. Keep your eyes and ears open. And it's very important that you should be part of a team. I said about 60 scientists, 60 personnel, and 30 engineers and scientists were all together as a team. Very important. And good work cannot be done in today's world without a collaboration. Try to make your bond stronger and become a great collaborator. And very important that you should always have scruples, which are very important. You should have faith in the principles of both science as well as ethics. And always we have to delve deep into the basics, which is very interesting. Do not study just for the sake of examination. And we should never get confined to a particular point. There is nothing like which you cannot understand. You can be a student of chemistry, still you can read a bit of physics. If you're a physicist, you can still learn chemistry and so on. We have all learned a lot of engineering, even though my fundamental training was only in chemistry. And luck favors only the prepared mind, said Pasteur. And Feynman said, hard work is the element of a great scientist. So what is very important for a scientist is to work on important problems. You cannot work on impertinent problems which nobody cares. You should be prominent. Therefore, you should pick up very important problems. And you should study why people are succeeding. You should study the success stories very closely. And you should know how did they succeed, what were the elements in their work, and what is your own style. What could be your own style, but make your style very distinct. And as they say, open mind is very important, and open mind is the open door which causes the one which so far not known to be known. And you should always try to do the best in whatever you do. You drink the best coffee, you drink the best tea, you make the best tea, you make the best coffee, you live at the best place, clean up your room the best way, write the best way possible, speak the best way possible, everything the best. So excellence, strive always towards excellence, even from small things. It's very important. A successful scientist becomes administrators, but at no point in time, you should be overconfident about anything. And what is the objective of research? So the objective of research is to get to the final point of creative thinking. And another very important point, which one of the writers, Sujata, also had said, Richard Hamming also says, do not waste your time on reading useless magazines if you want to have a serious career in science. So do not waste your time doing WhatsApp. I'm not saying you should not do WhatsApp, but time on WhatsApp should be minimized. And review books, articles, you need to spend a lot of time. I had a wonderful student of mine who's right now in the University of Florida, and he used to spend a lot of time, and he was very successful as compared to the others. 14 hours a day he used to read, and most of the literature survey I had was through him. So always people who work harder, who do not spend much time with the phones and with things which are useless otherwise for the technical work, are much more successful. Actually, the right problem at the right time, the right way needs to be done. It's not necessary you have to do something very fast, but you have to do something very correct. That's much more important. And creativity is very important. As I told you, even in a small thing, try to be very creative. Do something different. Do something that excites you, not something crazy, but something very different, which is usefully different, where you yourself are very appreciative of that. And you absolutely have to hone your skills. You should always learn new things. That keeps you going. They say every 7 years you're supposed to change your field of work. That's what the most famous scientists have said. Updation in your own field is also very important, and you should try to tolerate ambiguity. When there is something which you don't understand, yeah, it's okay, that doesn't matter, but there is a day when I'll understand, but let the ambiguity be there. Always get reminded of that. So any progress will definitely require constant change. That means you have to look inwards, reflect on yourself, and then you should work on that. That's very important. So these are the fundamental tenets which I thought are very relevant to my own career, which I learned from all other great thinking minds. So with a few words, I think I'll close my talk and open it for discussions. So what do you think is great? Is what you think is great is only great. So you be passionate. I wish you every success in your career. Thank you very much.
Thank you, sir.
Thank you, sir. That was a really informative talk. Now we'll address the questions asked by the attendees.
Sure.
Please post your questions if you have any in the comment section.
Yeah, any question will be entertained, no problem. It may not have to be relevant to the talk. Anything. Oh yeah, comments, something is coming up. Okay, thanks a lot for a wonderful introduction to DA institutes and the country, and in particular, I really loved your educating all of us about the giant of a man and scientist, Dr. Homi Bhabha, at the beginning of the talk. Okay, thank you.
You can also unmute yourselves if you want to ask any question to the sir directly.
Yeah, in fact, two scientists, namely, yeah, and Gillespie and Nelholm visited India. They were known for their theory on valential electron pair repulsion theory, which is very interesting. And one of them, after paying visits to many of the schools and colleges in India, he had a comment to make. The comment was very simple. You know, my professor U.R.K. Rao told me when I was in BRC training school, a student myself. So he told me, not a single guy asked a question. So I think our educational system doesn't promote us to question. So yeah, I think we should question. It can be, there's nothing like a silly question or anything. Any question is a question. I think you should learn to question.
So there is a question from
Yeah,
Gautam
that's a
SK.
question. Even though India had such a great advocate for the use of nuclear energy, India still is in the list on top nations using nuclear power. Yeah, but the question is right and wrong. It's right in the sense like we're not on the top in terms of the relative percentage of the energy that is produced compared to the overall consumption of nuclear energy in India. However, I would like to say like the amount of energy that India needs is much higher. So it's normally calculated based on the per capita consumption of energy. You take the energy produced divided by the number of persons in the country. So number of persons are quite huge. It's one of the most populous nations. Therefore, relatively, we are kind of less. But however, there are no countries in the world as of today which is having an active fast reactor program that's being pursued. In the different facets of nuclear energy, India is the only country which has got many institutes which are working on it. So Indian nuclear energy program is very vibrant and alive. Even China hasn't had its first nuclear reactor, excepting Russia. No other country is having a reactor which is running. In fact, the whole world is looking up to PFBR, the prototype fast breeder reactor, which has to be commissioned shortly in India. So India is really, in that sense, right on top of the world. But then we need to make our strides. We need to make ourselves stronger. Indian nuclear submarines, yeah. Okay, so Indian nuclear scientists making, yeah, we already have Vikrant, which is already is being run with nuclear submarine. There's a special nuclear submarine research center which is also situated in South India, where there is a lot of research going on. So submarines are not very special in the sense submarines also use a nuclear reactor which is much smaller. The advantage is for filling up diesel or the fuel, the submarine doesn't have to come up the to the surface. That's absolutely very important. And yeah, the new research by the Chinese government scientists to develop a nuclear reactor which does not require water to cool down by using liquid thorium instead of uranium. Can you tell us how is it possible? No, it's not like that. There is nothing like a liquid thorium cooled reactor. Normally, what is cooled, you can use either a liquid metal like sodium, or we can use water, one of the two. Even carbon dioxide can be used for cooling. There's nothing new in that. So uh, as far as the nuclear reactor technology is concerned, every nation in the country, in the world, they are following the same set of technologies which are commercially viable. In the nuclear technology, it's very difficult to come and throw open something altogether new because it has to be approved by for its safety and radiological aspects by special regulatory bodies. So it's not going to be easy for us to establish new systems just like that. So what are the Chinese are talking about? They're just a standard kind of fast reactors only. Medical cyclotron. Yeah, medical application of radiation are too many. You right from the cancer therapy, which is known to all, cobalt-60. Similarly, there are special isotopes which need to be made for treating. Now in today's world, they talk about targeted drug delivery. So when you have a diseased cell, a cancerous cell, we don't want to affect the radiation to go and affect other cells which are non-cancerous. So they put these radionuclides into certain chemicals, biochemicals, which can go into your system, which can be administered to the patient and can go to specific regions and attack the cancerous cells. This is one. Second important thing is there's something called as positron emission tomography, for which also we need to use special isotopes. All this could be produced. And there are bone pain palliatives for people suffering metastasized cancer. Basically, what happens is cancer grows to the stage 1, 2, 3, and 4. In the fourth stage, it spreads all over the body. At the time, the patient cannot be saved. However, we can reduce the pain of the patient, and for that, strontium-89 is one of the nuclides which could be produced. So the medical cyclotron is used for producing such exotic isotopes which are not naturally available. So basically, that's the purpose of the medical cyclotron. And Arihant is a nuclear submarine. Yeah, Arihant, you're right. It is not Vikrant. You're right, absolutely right. So interesting and informative talk. Okay. How are the nanocrystalline nuclear materials mentioned in your talk different from the other nuclear materials? What they are used for? Yeah, very simple. Nanocrystalline materials have is absolutely important because see, nanocrystalline materials have certain important properties. One is they have very high strength at a high temperature. Second thing is there is one thing that you need to do in the case of nuclear materials. We have to have very high dense tablets or the pellets which is used in the nuclear reactor. So densification of the ceramic materials usually require very high temperature. So when you use high temperature, you need to pump in more electricity, which means the process becomes very expensive. So if you can reduce the temperature of densification, which we call as temperature of sintering, then it can be a cost saving. So the nanocrystalline materials literally can be densified at much lower temperatures, something like 400, 500 degrees Celsius. The normal material is normally densified at a temperature of around, let us say 1600. Then this material can be densified at about 1000 degrees or 1200 degrees. That saves a lot of money and cost and effort. Therefore, this is absolutely very fantastic. And also there are certain other applications, like we want to specifically have certain microstructure, there is substructure within the material to be in a particular form so that that can be employed for the final application. Again, that can be done with the nanocrystalline powders. That's why nanocrystalline materials are very important. Yeah, Dr. Desikan, who's my colleague, who's also alumnus of your university, says, how do you see the collaboration between DAE and other universities like Hyderabad Central University happen. We actually welcome. And also, I want to use this forum and the platform to tell all the students, you're most welcome to come out to Kalpakam and do your summer projects. And we do have only restriction is you need to be with us for about 3 months, then you can do. And also, we organize what's called as a summer training in chemistry, where which we pay you stipend and we select students based on the write-up or the statement of purpose that you write, and you're trained and exposed to the different areas of research at Kalpakam by lectures, and you do also a little very small project, and it's a fun time for you. It's like a summer course. So I think I welcome all the students to apply for this. For a couple of years we could not do it because of the corona restriction. Probably from this 22 onwards we'll start it again. And yeah, collaborations are always open. There are many students from all over the country who come to us and do their projects, and they also get good publications, and that gives them an opening in the Department of Atomic Energy, and they get to know the process of recruitment. And if they want to pursue a career in nuclear energy, what is the way to go about, they understand. In addition to that, people who have completed their MSCs also have another way of applying for. Already I'm sure you will be knowing, you can become junior research fellow, so you can do a PhD here under Homi Bhabha National University. Some of my students have meritoriously done it. They also won good awards, and one of my students is right now, as I told you, placed in the University of Florida as and today as I speak to you. Any important training offered at DA units to students present days? Yeah, we are offering a lot of training is being offered to them. I said one is a summer training in chemistry. The second important thing is, of course, the JRF and SRF. There are so many methods by which we can train them. And also they can also do their MSc project work, which normally, if it's an industrial project, if the college permits them to be away for 3 months, they are most welcome. In fact, many of the students ended up joining us much later in their career, and many of them even got postdocs and they're not with us now. And HBNI, one good thing is, if you graduate from HBNI, you will not be absorbed in the atomic energy. We believe in diversity, and invariably you people get different kinds of a fellowship from some other country, and the success rate has been so good. So it'll give a good opportunity, and HBNI has been one of the top rated universities in the country. It is at par with the IITs as far as the postgraduate research in various faculty are concerned. We allow people to work on material science, people to work on chemistry, all the faculties of engineering, most of them in fact, metallurgy, electrical, mechanical, and chemical. We have a good battery of chemical engineers with us who are working on the reprocessing program at IGCAR as well. And there's a very strong materials engineering program. I do not want to go into the details of it because it's a mixed crowd. I don't know if I keep talking about certain areas, certain others may not like it. So I had to cover the entire people. So I left it to the question and answer session wherein I can explain the whole thing to you if you're interested. So you can ask me any specific questions in terms of the diversification that's possible within the Department of Atomic Energy. Is the technology developed at IGCAR to produce boron transfer to other DA units? No, the technology produced for producing boron is it's a local technology. Basically, this is meant for the in-house use by DAE. So the Heavy Water Board had been doing it, and the technology is already available with them. So the technology has been transferred properly. But we can't sell this technology because the material is a strategic material. That's another very important issue. There are certain materials which are called as strategic materials, which no country would like to import or export. So in such cases, you are compelled to develop a technology, which is very important. Sometimes you have the restrictions that you won't be able to publish even the results. But yeah.
So we have a question for you from Team JSC. Like,
Sure.
what made you to choose nuclear research?
Yeah, like what made me to choose was I was very fond of Bhabha Atomic Research Center, and I wanted to pursue chemistry, in fact, research in chemistry. But then Bhabha Atomic Research Center gave me both. It gave me a job at the same time. It gave me the avenue to do my research. So I joined the Bhabha Atomic Research Center. In those days, the training on many areas, including on computers was not available elsewhere. So we were at the frontier of research. Almost our entire MSc we completed within 1 year again. So there is that intensive training, and I really loved it. Then I came to Kalpakam. I started working on problems which were at the between interface between both chemistry and metallurgy, and also some material science aspects. So it was all entirely Greek and Latin to me, but then that's very enjoyable. Now, after 35 years, when I look back, I'm extremely happy about what I did, because I made a very vital contribution to the nuclear energy program of this country. So in terms of publications, in terms of our career growth also, it's been very good. So why did I choose atomic energy? Because I basically chose atomic energy because I wanted to do higher research in chemistry, and there were enough avenues available in atomic energy, which continues to be so. In fact, many of my colleagues, my contemporaries and peers are highly accomplished in fundamental chemistry research as well.
Okay, sir. So there is one more question in the comment section by Damodaran. What
Yes.
was the driving force for Dr. Homi Bhabha's vision of three-stage nuclear power program? And is it very important to present India?
Yeah. I've told you already about that. Jawaharlal Nehru and Baba had a very close discussion. They had a very good understanding as well. So Baba was concerned that at that particular point in time, there were two things happening. The atom bomb had exploded, and then there was a compulsion on the part of the United States to develop the technology so that they can demonstrate atomic energy is not for destruction. It is only for peaceful use of atomic energy. It's only for the peaceful uses. So therefore, the UN also passed a resolution. They formed the International Atomic Energy Agency. So in all, they had to go ahead and then find out a methodology by which atomic energy can be effectively harnessed. But then Baba immediately, he was very quick in his thinking. That's why he's called a visionary. He understood that the uranium mining in India was very poor. The ores were not there as on that day. However, we had a lot of thorium. The British were exporting a lot of thorium from our seashores to other countries and so on. In those days, they were using thorium for making mantles, gas mantle lamps, for which is very, very important. So all this made Baba to think that we should have a sustained energy program. And we were just at the early days of independence. India was in poverty. We did not have enough power producing mechanisms. The technology was very down. Whereas in nuclear technology, the installed capacity, the power density as they call it, with small amount of fuel, you can produce lot of energy. Therefore, he thought that's an amazing method by which the country can progress very fast. Time was a concern then. Therefore, they thought this will be very, very important. That's how Baba, in fact, one of the days when he got down from the car, suddenly he realized we're going to build a lot of pressurized heavy water reactors. But then, well, what are we going to do with the heavy water? So then suddenly it came to him. He went there and then made a note, and then he formed the heavy water board. Now he established something like 4 to 5 heavy water. Initially, it was only one plant, and then they multiplied. Now we have a heavy water surplus in the country. Now the heavy water board is doing all other things other than production of heavy water as well. So this is something very interesting. So visionaries and people who have a long-term thinking, they are able to do this. How is nuclear fusion research in India taking place? How is DAE aiming to accomplish excellence in this field? Yeah, basically the nuclear fusion research is an area, Institute of Plasma Research at Ahmedabad, and as well as the RRCAT. These are the two agencies which are involved in particle physics. Basically, most of nuclear fusion research will involve particle accelerators as well. So, however, world over, there has not been much of success in commercializing fusion research. So there is a common project called as ITER, which is being pursued in France. So India is a partner in ITER, and DAE scientists regularly go there on deputation, and they also contribute towards this. So if ITER comes through, the entire world will be benefited. So India also would be benefited to its part. Other than that, for the fundamental side, both for the plasma side as well as the particle physics side, India has enough research centers, namely the Variable Energy Cyclotron Center. And also we have the RRCAT, which is a big unit that's been established for the sake, which also works on lasers. And then we have also the Institute of Plasma Research, which is working on this.
I hope there are no more questions from the audience side.
All right, so it's been a long time. Yeah, thank you very much.
Yes.
Thank you so much.
On behalf of the Junior Science Club, I would like to extend a hearty vote to the Honorable Speaker, Dr. Ananta Shivan, who very graciously shared his virtual presence and took out valuable time from his busy schedule to share his knowledge with us. It was a pleasure listening to your talk, sir. I also wish to express my gratitude to the Director of the College of Integrated Studies, Professor B.V. Sharma, and to the Associate Director, Professor Salman Abdul, for providing us this opportunity and support to organize this talk. I'm very grateful to all the faculty coordinators of JSC, Professor Ilingovan, Professor Rachana Maurya, Professor Muralidharan, Professor Srinath, and Professor Manjari for their constant presence, guidance, and valuable encouragement. At last, I extend a big thanks to our CIS office members, all the seniors and fellow student coordinators of JSC, and our dear audience for participating with such enthusiasm and patience. Thank you all for making this event successful with your contribution.
Thanks
With
a lot.
this, we have reached the end
Yeah,
of this talk. Thank you, everyone.
thank you. It is a pleasure too. I also thank all the audience for being patient, and still many of them are on board. Thank you very much. Have a great weekend. Bye bye. And happy
Thank you, sir.
Diwali for those who are going to celebrate it. Thank you very much. Bye bye.